As you settle into your bed tonight, feeling the soft fabric against your skin and breathing in the familiar air of your room, you might imagine that you're surrounded by solid, unchanging matter. The pillow beneath your head feels firm and stable. The air you breathe seems like empty space, occasionally stirred by a gentle breeze. But if we could shrink down, smaller than the tiniest microscope can see, we'd discover that you're actually resting in the middle of the most elegant, eternal dance imaginable. Every thread in your sheets, every molecule of oxygen you breathe, every atom in your own body is part of an invisible ballet that has been performing for billions of years. Tonight, we're going to join that dance, beginning our journey in this familiar bedroom and traveling inward, deeper and deeper, until we discover the secret lives of the atoms that make up everything you see, touch, and are. Take a gentle breath and feel your chest rise. In that single breath, you've just welcomed approximately 25,000 trillion molecules into your lungs. Each one of these molecules is composed of atoms so small that if you could line up 100 million of them side by side, they would span just 1 centimeter. Yet, despite their incredible tininess, these atoms are not empty space. Each one is a universe unto itself, with a dense nucleus surrounded by clouds of electrons moving in patterns so rapid and intricate that they create the solid matter we experience. The carbon atoms in your body right now, in your muscles, your bones, your brain, these same atoms once danced inside ancient stars. Billions of years ago, in the heart of a dying star many times larger than our sun, intense heat and pressure fused lighter elements together, forging the carbon that would eventually become part of you. When that star finally exhausted its fuel, it scattered these newly created atoms across space in a spectacular explosion, seeding the cosmos with the building blocks of life. Those carbon atoms drifted through the cold vacuum of space for millions of years before gravity began to gather them, along with hydrogen, oxygen, and other elements, into the cloud that would eventually become our solar system. They were present when Earth first formed from cosmic dust and rock, and they've been cycling through countless forms ever since, sometimes locked in ancient rocks, sometimes flowing through prehistoric oceans, sometimes part of the first simple life forms that emerged in Earth's primordial seas. The iron in your blood has an even more dramatic origin story. It was forged in the core of a massive star during the final moments of that star's life, when temperatures reached hundreds of billions of degrees. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, all of these elements share similar cosmic journeys, traveling across vast distances and spans of time to eventually become part of the miracle of your existence. But atoms don't simply travel, they interact, combine, and create. The hydrogen atoms in the water you drank today are among the oldest things in the universe, formed just a few minutes after the Big Bang, when the cosmos was still young and hot. Yet, despite their ancient age, these hydrogen atoms remain as active today as they were billions of years ago, forming bonds, breaking apart, and forming new connections with the enthusiasm of cosmic dancers who never tire. Right now, as you lie in your bed, your body is conducting millions of chemical reactions every second. In your liver, alcohol dehydrogenase molecules are carefully dismantling any alcohol molecules you might have consumed, breaking them down into harmless components through a process so precise it resembles molecular surgery. In your muscles, creatine kinase enzymes are regenerating the energy currency your cells need to function, transferring phosphate groups with the precision of master craftsmen. Your brain, even as it begins to relax into sleep, remains a symphony of atomic activity. Sodium and potassium atoms are flowing across neuron membranes, creating electrical signals that carry thoughts, memories, and dreams. Dopamine molecules, each composed of just 43 atoms, are binding to specific receptor sites with a lock and key precision that influences your mood and sense of well-being. Consider the remarkable fact that you are, quite literally, a collection of atoms that has somehow organized itself to be conscious of atoms. The calcium phosphate crystals in your bones provide structure, while the protein collagen fibers woven between them provide flexibility. A partnership between mineral and organic that creates a material stronger than many artificial composites. Your muscles contract through the sliding of protein filaments past one another, powered by molecular motors that convert chemical energy into mechanical motion with an efficiency that surpasses any human-made engine. The air around you, which seems so empty, is actually filled with molecules moving at hundreds of meters per second, constantly colliding with each other and with the surfaces in your room. Oxygen molecules, each composed of 2 oxygen atoms sharing electrons, in a bond so strong it requires intense heat or special enzymes to break, are waiting patiently to participate in the slow combustion that powers your cells. Water molecules in the air are performing their own graceful dance, their slightly bent shape giving them a positive side and a negative side, like tiny molecular magnets. This simple property allows them to form temporary bonds with each other, creating the surface tension that holds water droplets together and the humidity you feel on particularly moist evenings. As we prepare to journey deeper into the atomic realm, remember that this invisible world operates according to principles both familiar and strange. At the scale of atoms and molecules, the sharp distinctions we're used to between solid and liquid, between one substance and another, between self and environment begin to blur. What we find instead is a world of probability, cooperation, and constant change, where the same carbon atom might spend part of its existence as carbon dioxide in the atmosphere, part as sugar in a plant, and part as a component of your own DNA. The atoms in your left hand right now have no way of knowing they're part of your left hand rather than your right hand, or part of you rather than part of the pillow beside you. They simply follow the laws of physics and chemistry, forming bonds when conditions are favorable, releasing energy when reactions are thermodynamically permitted, and participating in the vast molecular ecosystem that makes life possible. Tonight, as you begin to drift towards sleep, your atomic constituents will continue their ancient dance. Some of the carbon dioxide you exhale will be absorbed by plants outside your window, beginning a new phase of the carbon cycle. Some of the water molecules you're losing through your skin will evaporate and join the atmospheric water cycle that has been operating for billions of years. You are not separate from this atomic world. You are this atomic world, temporarily organized into a pattern that thinks and feels and wonders. As we continue our journey, we'll explore how these microscopic dancers create the biological processes that sustain your life, the chemical bonds that hold matter together, and the quantum mechanical principles that govern the behavior of electrons and nuclei. But for now, simply rest in the knowledge that you are part of something magnificent and ancient and ongoing. The atoms in your body have survived the death of stars, the formation of planets, and the emergence of life itself. They have been part of countless other forms, perhaps once part of a towering redwood tree, a swimming dolphin, or a grain of sand on a prehistoric beach. Tomorrow, some of these atoms will begin new journeys, but tonight they are you, participating in the quiet miracle of consciousness, in this moment of peaceful reflection on the invisible foundation that makes all experience possible. The gentle giants. As you continue to breathe slowly and deeply, let's focus on that breath itself and meet the gentle giants that make life possible. These are the common elements, oxygen, carbon, hydrogen, and nitrogen, that form the foundation of all biological existence. Despite their incredible importance, they work with quiet humility, never demanding attention for their essential roles in the drama of life. With each inhalation, approximately 500 trillion oxygen molecules enter your lungs. Each oxygen molecule consists of 2 oxygen atoms that have chosen to share electrons in one of nature's most stable partnerships. This sharing isn't a violent seizure of electrons, but rather a gentle cooperation where both atoms become more stable and content than they would be alone. Oxygen atoms are particularly generous partners. With 6 electrons in their outer shell, but space for 8, they eagerly form bonds with other atoms that can help complete this stable configuration. When 2 oxygen atoms meet, they share 2 pairs of electrons, creating what chemists call a double bond. Imagine 2 dancers holding hands with both their left and right hands moving in perfect synchronization. But oxygen's generosity extends far beyond its relationship with itself. Right now, in the mitochondria scattered throughout your body, those tiny cellular power plants inherited from ancient bacterial ancestors, oxygen atoms are participating in the careful, controlled combustion that powers your life. They're combining with hydrogen atoms stripped from sugar molecules, forming water and releasing energy in a process so efficient and gentle that you never feel the fire that sustains you. This cellular respiration is nothing like the violent combustion of a campfire. Instead, it's more like a carefully choreographed dance where electrons are passed from partner to partner along a chain of protein molecules embedded in the mitochondrial membrane. Oxygen waits patiently at the end of this electron transport chain, ready to accept the electrons and combine with hydrogen to form water. It's a process that occurs billions of times per second in your body, yet it unfolds with such precision that the energy is released gradually, warming you gently rather than burning you up. Carbon, meanwhile, is life's master architect. With 4 electrons in its outer shell and room for 4 more, carbon atoms can form 4 bonds simultaneously, creating complex 3-dimensional structures with an elegance that surpasses any human engineer. The carbon atom sitting in your brain right now might have 4 bonds extending in different directions, one connecting to a hydrogen atom, one to a nitrogen atom, one to another carbon atom, and one to an oxygen atom, creating a molecular sculpture that serves as part of a neurotransmitter molecule. What makes carbon so special is its perfect balance between stability and flexibility. Carbon bonds are strong enough to hold large molecules together, yet flexible enough to allow the molecular movement necessary for biological processes. The carbon chains that form the backbone of fatty acids can bend and flex like microscopic serpents, allowing cell membranes to maintain their fluid properties. The carbon rings in DNA bases can resonate between different electron configurations, fine-tuning their ability to recognize complementary bases through hydrogen bonding. Consider the carbon atom that's part of a glucose molecule in your bloodstream right now. This atom began its current journey when a plant captured carbon dioxide from the atmosphere during photosynthesis. In the plant's chloroplast, solar energy was used to strip the carbon away from two oxygen atoms and incorporate it into a sugar molecule. That sugar traveled through the plant's vascular system, perhaps ending up in a fruit that you ate for lunch. Now, as this glucose molecule encounters an enzyme in your liver, the carbon atoms are being carefully rearranged. Some being stored as glycogen for later use, others being converted into fat molecules for long-term energy storage. Each transformation involves the breaking and forming of bonds with the precision of molecular origami, guided by proteins that have evolved over billions of years to catalyze these reactions with extraordinary specificity. Hydrogen, the universe's simplest atom with just one proton and one electron, might seem unremarkable, but it plays crucial roles in biological chemistry. Hydrogen atoms love to form weak bonds called hydrogen bonds, gentle attractions between a hydrogen atom attached to one molecule and an electronegative atom on another molecule. These bonds are much weaker than the covalent bonds that hold atoms together within molecules, but they're strong enough to give water its unique properties and to hold the two strands of your DNA together in their famous double helix. The hydrogen bonds in water create a network of temporary connections between molecules, allowing water to remain liquid at Earth's surface temperatures, while also giving it the ability to dissolve a remarkable variety of other substances. Right now, the water in your cells is forming and breaking about 1 trillion hydrogen bonds every second, creating a dynamic liquid environment that allows proteins to fold into their proper shapes and enables the molecular encounters necessary for biochemical reactions. In your DNA, hydrogen bonds between complementary base pairs, adenine with thymine, guanine with cytosine, hold the two strands of the double helix together with just the right strength. These bonds are strong enough to maintain the DNA's structure, yet weak enough to allow the strands to separate when the cell needs to copy the genetic information or create RNA molecules for protein synthesis. Nitrogen, though often overlooked, makes up about 78% of the atmosphere around you. Most nitrogen exists as N2 molecules, two nitrogen atoms, joined by a remarkably strong triple bond that makes them largely unreactive under normal conditions. This stability is actually beneficial, creating an inert buffer gas that dilutes oxygen and prevents our atmosphere from being so reactive that everything would spontaneously combust. But when nitrogen does participate in biological chemistry, it plays essential roles. The nitrogen in your amino acids, the building blocks of proteins, came from nitrogen that was fixed by specialized bacteria, either living freely in soil or in partnership with legume plants. These bacteria possess the remarkable ability to break nitrogen's triple bond and incorporate nitrogen atoms into biological molecules, making them available to the rest of the living world. The nitrogen in your DNA bases forms additional hydrogen bonds that help stabilize the double helix. In your proteins, nitrogen atoms in the amino acid backbones form peptide bonds, strong, stable connections that link amino acids together in long chains. These chains then fold into complex three-dimensional shapes, guided by interactions between the various side chains that extend from the backbone. Every breath you take brings you into intimate contact with these gentle giants. The oxygen you inhale will soon be incorporated into water molecules and carried in your bloodstream. The carbon dioxide you exhale carries carbon atoms that were recently part of sugar molecules broken down for energy. Even the nitrogen you breathe in and out, largely unchanged, serves as a reminder of the vast reservoir of potential biological building blocks surrounding you. These four elements, oxygen, carbon, hydrogen, and nitrogen, make up about 96% of your body's atoms. Yet, they don't exist in isolation. They're constantly forming temporary partnerships, breaking apart, and forming new alliances in the ongoing molecular dance that sustains your life. An oxygen atom that's part of a water molecule in your blood plasma might soon become part of a carbon dioxide molecule in your lungs, then part of the atmospheric CO2 that a plant will incorporate into a sugar molecule next week. As you prepare to drift deeper into sleep, consider the profound interconnectedness these elements represent. The oxygen atoms keeping you alive right now were created in the core of massive stars billions of years ago. The carbon atoms in your DNA have been cycling through the biosphere for millions of years, sometimes part of ancient marine organisms, sometimes dissolved in primordial oceans, sometimes locked away in limestone deposits, and now temporarily part of you. The hydrogen atoms in the water in your cells are among the oldest things in existence, formed when the universe was just a few minutes old and much smaller and hotter than it is today. The nitrogen in your proteins links you to the vast atmospheric reservoir that has been maintained by the balance between nitrogen fixation and denitrification for billions of years. These gentle giants work together with such seamless cooperation that we rarely notice their constant activity. They form the molecular foundation that makes consciousness possible, yet they operate according to simple physical and chemical principles that have remained unchanged since the universe began. As we continue our journey into the atomic realm, we'll discover how these elements combine to create the more complex molecular machines that orchestrate the processes of life. The molecular artists. Now that we've met the gentle giants that form life's foundation, let's witness how they collaborate to create the molecular masterpieces that make your existence possible. As you rest comfortably, your body is hosting millions of molecular artists, each crafting intricate structures with a precision and beauty that surpasses any human creation. Begin with the water that makes up about 60% of your body weight. Each water molecule is a simple yet elegant sculpture. Two hydrogen atoms bonded to one oxygen atom in a bent configuration that creates a molecule with personality. The oxygen atom, slightly greedy for electrons, pulls the shared electrons closer to itself, leaving the hydrogen atoms with a small positive charge and giving the oxygen a small negative charge. This molecular personality allows water molecules to form weak but meaningful connections with each other and with other molecules. Right now, in the fluids surrounding your cells, water molecules are engaged in a constant dance of temporary partnerships. Each water molecule can form up to 4 hydrogen bonds simultaneously, 2 through its hydrogen atoms and 2 through lone pairs of electrons on its oxygen atom. These fleeting connections create networks that last for just trillionths of a second before dissolving and reforming elsewhere. Yet this constant networking gives water its remarkable properties. It can dissolve salts by surrounding individual ions with shells of oriented water molecules, each water molecule carefully positioning its positive or negative end toward the dissolved ion. It can form the liquid medium in which your proteins fold into their proper shapes, supporting some parts of the protein structure while allowing other parts the freedom to flex and move. The water in your cells is never just water. It's a complex solution containing thousands of different dissolved substances, each interacting with water molecules in specific ways. Glucose molecules form hydrogen bonds with water, keeping them dissolved and available for cellular energy production. Amino acids extend different chemical groups into the water, some loving the aqueous environment and others preferring to hide away from it. Moving from the simple elegance of water to the breathtaking complexity of DNA, we encounter one of nature's most sophisticated molecular sculptures. Your DNA is constructed from just 4 types of building blocks, the nucleotides containing adenine, thymine, guanine, and cytosine. Yet, the way these components are arranged encodes all the information necessary to construct and maintain your body. Each nucleotide is itself a work of molecular art, consisting of a sugar molecule, a phosphate group, and one of the 4 bases. The sugar molecules form the backbone of each DNA strand, linked together by phosphate bridges in a repeating pattern that creates a stable, flexible framework. Extending from this backbone are the bases, each one a flat molecular structure containing rings of carbon and nitrogen atoms, with precisely positioned hydrogen bonding sites. The genius of DNA lies in the complementary base pairing. Adenine forms exactly 2 hydrogen bonds with thymine, while guanine forms exactly 3 hydrogen bonds with cytosine. This specificity means that the 2 strands of the double helix are perfectly complementary. Wherever one strand has an adenine, the other has a thymine, and vice versa. The result is a molecule that can store information in the sequence of bases along one strand while maintaining a backup copy in the complementary sequence of the other strand. Right now, as you breathe peacefully, specialized molecular machines are moving along your DNA, reading the genetic instructions and using them to direct the synthesis of RNA molecules. These RNA polymerase enzymes work with extraordinary precision, moving along the DNA strand, one base at a time, unwinding the double helix just enough to read the template strand, and synthesizing a complementary RNA copy. The RNA molecules themselves are molecular artists in their own right. Unlike DNA, RNA typically exists as a single strand, but this apparent simplicity allows for remarkable creativity. RNA strands can fold back on themselves, forming complex three-dimensional structures with loops, stems, and bulges. Some RNA molecules, called ribozymes, can even catalyze chemical reactions, serving as both the blueprint and the craftsman in certain cellular processes. But perhaps the most impressive molecular artists in your body are the proteins. Each protein is a unique sculpture created from a linear chain of amino acids that folds into a specific three-dimensional shape. The folding process is itself a wonder to behold. As the newly synthesized protein chain emerges from the ribosome, it begins to search for its most stable configuration, trying different conformations until it settles into the shape that minimizes its energy. This folding process is guided by the chemical properties of the amino acid side chains. Hydrophobic amino acids, which dislike water, tend to cluster together in the protein's interior, while hydrophilic amino acids position themselves on the protein's surface, where they can interact favorably with the surrounding water. Positively charged amino acids seek out negatively charged partners, while amino acids capable of forming hydrogen bonds position themselves to take advantage of these weak interactions. The result is a molecule with a precisely defined shape and a specific set of chemical capabilities. An enzyme protein might have a cleft or pocket that exactly matches the shape and chemical properties of its substrate molecule, allowing it to bind the substrate and facilitate a particular chemical reaction. A transport protein might undergo conformational changes that allow it to pick up molecules on one side of a cell membrane and deliver them to the other side. Consider the hemoglobin molecules in your red blood cells right now. Each hemoglobin molecule is composed of 4 protein subunits, each containing a heme group with an iron atom at its center. The protein portion of hemoglobin creates exactly the right environment for the iron atom to bind oxygen molecules loosely in your lungs and release them readily in your tissues. The protein structure also allows the 4 subunits to communicate with each other, so that binding of oxygen to one subunit increases the likelihood that the other subunits will also bind oxygen, a phenomenon called cooperative binding that makes hemoglobin far more efficient than it would be if the subunits acted independently. Lipid molecules represent another class of molecular artists, specializing in the creation of biological membranes. Each phospholipid molecule has a hydrophilic head group that loves water and 2 hydrophobic fatty acid tails that prefer to avoid water. When placed in an aqueous environment, these molecules spontaneously organize themselves into bilayers, with the hydrophilic heads facing outward toward the water and the hydrophobic tails clustering together in the interior. This simple self-assembly creates one of biology's most important structures, the cell membrane that separates your cell's interior from the external environment. But lipid membranes are not static barriers. The fatty acid tails can rotate and flex, giving the membrane a fluid quality that allows proteins to move within the membrane and enables the membrane to bend and flex as cells change shape. Some membrane proteins span the entire bilayer, creating channels that allow specific molecules to pass through the membrane. Others are embedded partially in one side of the membrane or the other, serving as receptor sites for molecular signals or as anchoring points for cellular structures. The result is a dynamic, responsive boundary that maintains cellular integrity while enabling controlled communication and transport. The molecular artists in your body work with materials that would be impossible to manipulate by hand, individual atoms and small groups of atoms. Yet they create structures of incredible precision and beauty. The active site of an enzyme might position several amino acid side chains with atomic level accuracy to facilitate a specific chemical reaction. A ribosome coordinates the movements of transfer RNA molecules, ensuring that amino acids are added to a growing protein chain in exactly the right sequence. Even as you prepare for sleep, these molecular artists continue their work. In your liver, cytochrome P450 enzymes are modifying foreign molecules, making them more water-soluble so they can be eliminated from your body. In your brain, neurotransmitter molecules are being synthesized, packaged into vesicles, and positioned for release at synaptic terminals. In your muscles, contractile proteins are maintaining the slight tension that keeps your body positioned comfortably as you rest. The beauty of these molecular sculptures lies not just in their individual complexity, but in their ability to work together in integrated systems. A single nerve impulse involves the coordinated action of dozens of different proteins, voltage-gated ion channels that control the flow of sodium and potassium ions across the neuronal membrane, enzymes that maintain the proper ionic gradients, proteins that package and release neurotransmitters, and receptors that detect and respond to these chemical signals. As we prepare to journey even deeper into the atomic realm to explore the quantum mechanical behavior that underlies all chemical bonding, take a moment to appreciate the molecular artistry that surrounds and comprises you. You are not just made of atoms. You are made of atoms that have organized themselves into molecular structures of extraordinary beauty and sophistication, each one a testament to the creative potential inherent in matter itself. As we journey deeper into the heart of matter, we enter a realm where the familiar rules of everyday experience give way to something far more mysterious and beautiful. Here, at the quantum level, we discover that the atoms composing your body are not tiny solid spheres, but rather clouds of probability, dancing to rhythms governed by the strange and wonderful laws of quantum mechanics. Close your eyes and imagine shrinking down to the size of an atom. What you would find is not the miniature solar system that early atomic models suggested, with electrons orbiting a nucleus like planets around the sun. Instead, you would discover something far more ethereal and magical. Electrons that exist as probability clouds, simultaneously present in multiple locations until the moment they interact with something else. The electrons in the atoms of your body don't follow definite paths. Instead, they exist in what quantum physicists call orbitals, three-dimensional regions where the electron is likely to be found. These orbitals have beautiful geometric shapes. Some are spherical clouds surrounding the nucleus. Others are dumbbell-shaped, with lobes extending in different directions. And still others have more complex forms, with multiple lobes and nodal planes, where the electron never ventures. Right now, in the carbon atoms that form the backbone of the DNA in your cells, electrons are occupying orbitals that overlap and blend with orbitals from neighboring atoms. When these orbital clouds overlap significantly, they create what we call chemical bonds, not rigid connections between solid particles, but shared regions where electrons can move freely between atoms, belonging simultaneously to both. Consider the oxygen molecule you just breathed into your lungs. Each oxygen atom contributes 2 electrons to form the double bond between them. But these 4 electrons don't belong exclusively to either atom. Instead, they exist in molecular orbitals that extend over both atoms, creating electron density in the region between the nuclei that holds the molecule together. It's as if the electrons are performing a dance that weaves the atoms together through their shared movement. The quantum nature of electrons gives them properties that would seem impossible in our everyday world. An electron has a property called spin, though it's not actually spinning like a tiny top. Quantum spin is more like an intrinsic magnetic orientation that can point either up or down. According to the Pauli exclusion principle, no 2 electrons in an atom can have exactly the same quantum state. They must differ in at least one quantum property. This exclusion principle is what gives atoms their size and prevents matter from collapsing into a dense point. The electrons in each atom must occupy different orbitals or different spin states, creating the electron clouds that define atomic dimensions. The resistance you feel when you press your hand against the bedsheet isn't really solid matter pushing back. It's the electromagnetic repulsion between electron clouds that refuse to occupy the same space. When atoms form covalent bonds, they're sharing electrons in a quantum mechanical embrace. The hydrogen atoms in a water molecule don't simply give their electrons to the oxygen atom, nor does the oxygen atom keep its electrons to itself. Instead, the electrons exist in molecular orbitals that encompass all 3 atoms, spending time near each nucleus, but belonging to the molecule as a whole. The sharing isn't always equal. In water, the oxygen atom has a stronger attraction for electrons than the hydrogen atoms do, so the shared electrons spend more time near the oxygen nucleus. This creates a partial negative charge on the oxygen atom and partial positive charges on the hydrogen atoms, giving water molecules their polar nature and enabling the hydrogen bonding that makes life possible. Even more fascinating are the quantum tunneling events occurring in your body right now. In classical physics, a particle needs enough energy to go over a barrier to get from one place to another. But in the quantum world, particles can sometimes tunnel through barriers that should be insurmountable. This quantum tunneling plays crucial roles in many biological processes. In the enzyme that copies your DNA, quantum tunneling allows protons to move between base pairs during the brief moments when the DNA strands are separated. Some scientists believe that quantum tunneling of protons might even be involved in genetic mutations, allowing hydrogen atoms to tunnel from their normal positions to alternative locations, temporarily changing the bonding patterns of DNA bases. The quantum effects become even more pronounced when we consider the behavior of electrons in aromatic molecules like those found in your DNA bases and many amino acids. In these molecules, electrons exist in delocalized pi orbitals, quantum states that extend over multiple atoms in ring structures. The electrons can move freely around these rings, creating molecular current loops that give aromatic compounds their special stability. In your retina right now, quantum mechanics is enabling your vision. When a photon of light strikes a molecule of rhodopsin in your rod cells, it causes an electron to jump from one quantum state to another, changing the shape of the molecule and initiating the cascade of biochemical events that your brain interprets as vision. The precise wavelength of light that can trigger this quantum transition determines which colors you can see. Quantum coherence, the ability of quantum systems to exist in multiple states simultaneously, might even play roles in biological processes that we're only beginning to understand. Some researchers suggest that the remarkable efficiency of photosynthesis might depend on quantum coherence effects that allow energy to explore multiple pathways simultaneously, always finding the most efficient route to the reaction centers, where light energy is converted to chemical energy. The magnetic field sensing ability of migratory birds appears to rely on quantum entanglement, a phenomenon where particles become connected in such a way that measuring one instantly affects the other, regardless of the distance between them. Special molecules in birds' eyes may contain pairs of electrons whose quantum spins remain entangled, creating a biological compass sensitive to Earth's magnetic field. But perhaps the most profound quantum effect in your body is the very existence of stable matter itself. The stability of atoms depends on the quantization of electron energy levels. Electrons can only exist in specific, discrete energy states, not in the continuous range of energies that classical physics would allow. This quantization prevents electrons from spiraling into atomic nuclei, maintaining the stable electron clouds that give atoms their properties. The chemical bonds holding your body together are quantum mechanical phenomena. When two hydrogen atoms approach each other to form a hydrogen molecule, their electron wave functions begin to overlap. Quantum mechanics allows for two possibilities. The wave functions can either add together constructively, creating a bonding orbital with electron density between the nuclei, or they can subtract from each other destructively, creating an anti-bonding orbital with a node between the nuclei. The electrons naturally occupy the lower energy bonding orbital, and the increased electron density between the nuclei creates an attractive force that holds the atoms together. This isn't a classical force like gravity or magnetism. It's a purely quantum mechanical effect arising from the wave-like nature of electrons and their tendency to occupy the lowest available energy states. Van der Waals forces, the weak attractions between molecules that help hold your cell membranes together and give water its surface tension, also arise from quantum effects. These forces result from temporary fluctuations in electron distributions that create instantaneous dipoles, brief moments when one side of a molecule becomes slightly more negative than the other. These temporary charge separations induce similar separations in nearby molecules, creating weak attractive forces that, while individually small, collectively contribute to the cohesion of matter. Even the thermal motion in your body, the constant vibrating and jiggling of atoms and molecules that maintains your body temperature, is governed by quantum mechanics. The vibrational energy of molecules is quantized, meaning that molecular vibrations can only occur at specific frequencies and energy levels. This quantization affects how molecules absorb and emit thermal energy, influencing everything from the infrared radiation your body emits to the efficiency of enzymatic reactions. As you settle into deeper relaxation, consider the profound implications of quantum mechanics for your existence. You are not a classical object obeying the deterministic laws of Newtonian physics. You are a quantum system composed of particles that exist in probability clouds, connected by bonds that arise from wave function overlaps, maintained by forces that emerge from the fundamental uncertainty and interconnectedness built into the fabric of reality itself. The quantum dancers that comprise your atoms are performing a ballet of probability and uncertainty, yet from their ethereal movements emerges the solid reality of your physical existence. The apparent contradiction between the fuzzy, probabilistic nature of quantum particles and the definite, concrete experience of being human remains one of the deepest mysteries in science. Tomorrow, when you wake up, the quantum dancers will still be there, still performing their probability ballet in the atoms of your body, still creating the stable matter that allows you to think and feel and wonder about the nature of existence itself.